Today, we're diving into the incredible systems that allow these gigantic machines to navigate our skies with just pinpoint precision. We're talking about flight control, the magic that makes it all happen.
I mean, it seems almost impossible, right? How can something so massive be so agile? Well, the answer is this kind of beautiful conversation that's happening between the pilot, the machine, and the air itself. So let's break down how that conversation actually works.
Okay, so to really get how to control an aircraft, we first need to figure out what flying freely even means. What are the basic movements we need to get a handle on?
And here they are, the three fundamental rotations of flight. You've got pitch, that's the nose tilting up or down. Then there's roll, where the wingtips dip from side to side. And finally, yaw, which is that side-to-side waggle of the nose. Seriously, every single thing a plane does in the air, it's just some combination of these three moves.
Okay, before we get into all the complexities of moving through air, let's simplify things a bit. Let's do a little thought experiment. How would you steer a vehicle in the complete vacuum of space?
Well, it all comes back to some really basic physics, right? Isaac Newton. To change anything, to rotate, to move, to stop, you have to push on it. You've got to apply a force. But in space, there's no air to push against, so you have to bring your own push.
And that push really comes in two main flavors. For the big, powerful movements, you use thrusters, basically tiny little rockets. But for the really delicate, precise adjustments, you use something called reaction wheels. They're wild. They generate force internally just by spinning.
So here you can see the two side by side. On the left, that's a thruster. It's all about brute force. But on the right, that's a reaction wheel. The ice skater analogy is perfect here. You know how they pull in their arms to spin faster? It's all about these really precise internal changes in momentum to turn the spacecraft. Super clever.
Okay, so that's space. Let's come back down to Earth. Obviously, we can't just be firing rockets all the time to steer a plane. That would be insanely inefficient. So the question becomes, how do we generate those same control forces using the one thing we have an absolute ton of, air?
And here's how we do it. Meet our first control surface, the elevator. It's that hinged flap you see on the horizontal part of the tail. And it's simple, really. When you move it up, the air flowing over it pushes the tail down. And when the tail goes down, the nose pitches up. It's a lever, just using air.
So the chain of events here is the key takeaway. The pilot pulls back on the controls. That makes the elevator move up. The air pushes the tail down, and the nose pitches up. It's just a beautifully simple lever system, with the air doing all the heavy lifting.
All right, so that's up and down. What about side to side? Well, for that, we have the rudder. That's the moving part on the big vertical fin at the back. It works the same way. You push the left rudder pedal, the rudder surface moves left, the air pushes the tail to the right, and that makes the nose yaw to the left.
So again, it's a really direct cause and effect thing. You push the left pedal because you want the nose to go left. Super intuitive, right? Okay, so that's pitch and yaw. Now let's tackle the last, and maybe the most interesting axis of movement. And that brings us to roll. This is handled by the ailerons, those flaps on the back edge of the wings. And this is where things get really clever, because they work in opposition to each other. To roll the plane to the right aileron actually goes up, which kills some lift on that wing, while the left one goes down, which increases lift. It's this imbalance of forces that actually rolls the whole plane. So cool.
So, it all seems pretty straightforward, doesn't it? You just point the controls where you want to go. But there's a huge critical difference between steering a car and flying a plane, and it's something that trips a lot of people up.
Okay, check this out. In a car, right? You turn the wheel 20 degrees to the left, and the car is now pointed 20 degrees left. You hold the wheel there, and you stay in that turn. Your input controls the angle. But in a plane, it's totally different. When you push the stick left, the plane starts rolling to the left. Your input controls the rate of the roll. So to hold a 20-degree bank, you have to push the stick left, get to that 20-degree angle, and then bring the stick back to the center to stop the roll. It's a huge fundamental difference.
So we've got this beautiful, elegant system of control surfaces. Elevators, rudders, ailerons. It all seems perfect. But, physics just loves to throw in a plot twist. And it turns out our really clever solution for rolling the plane, it comes with a super annoying side effect.
So, simple question, right? Think back to the ailerons. We said one wing creates more lift to start the roll. But what's the unavoidable byproduct of creating lift? What always comes along for the ride? Drag.
And that extra drag creates a really annoying problem called adverse yaw. Basically, the wing that's going up, the one with more lift, also has more drag, so it gets pulled back a little.
The result? As you try to roll the plane to the right, the nose actually tries to swing or yaw to the left. It's literally turning the opposite way you want it to. Not good.
But of course, engineers came up with some absolutely brilliant solutions. Solution number one is called the freeze aileron. Check this out. When the aileron moves up to decrease lift, its leading edge is designed to dip down into the airflow. What does that do? It creates a bunch of extra drag, on purpose, just to balance out the drag from the other wing. It's so smart.
And here's another, maybe even more elegant solution. Just automate the fix. Some planes have a mechanical linkage, springs and cables, that physically connect the ailerons and the rudder. So when the pilot moves the stick to roll, the system automatically puts in a little bit of rudder to cancel out that adverse yaw. The pilot doesn't even have to think about it. The plane just fixes it itself.
All right, so we've been talking about fixed-wing aircraft this whole time. But what about helicopters? Helicopters are a completely different beast. They have their own totally unique set of problems to solve.
And the number one biggest problem comes from our old friend Newton's third law. For every action, there's an equal and opposite reaction. So think about it. As the engine spins those huge main rotor blades in one direction, that same force, that torque, is trying to spin the entire body of the helicopter in the opposite direction. Without something to counteract that, a helicopter would just be a completely uncontrollable spinning top.
And what is so amazing is the sheer variety of clever solutions engineers have come up with for this one problem. You've got the classic tail rotor. It's basically a little propeller on its side just pushing back. Then there's the fenestron, which is a safer ducted fan inside the tail. Some, like the Nodar system, don't even have a tail rotor. They use a jet of air. And then there's maybe the coolest solution. Just add a second main rotor on top, spinning the opposite way. The two torques just cancel each other out. Problem solved.
So whether you're sculpting the air flowing over a simple wing, or you're trying to balance the insane torque of a spinning rotor, flight control is really just a constant, delicate conversation with the laws of physics. And it just makes you wonder, doesn't it? What incredible new things are engineers going to teach aircraft to say next?